Program analysis is credible when very few false alarms are produced. Abstract interpretation is sound by construction. That means that false alarms may happen. It is very unlikely that it is complete. Completeness holds when we have the most of precision from our analysis and no false alarms are produced, but this almost never happens. For input 10, the following three programs produce the same output. This doesn't hold if you have abstract interpretation with intervals. We will have different results. This is because we have incompleteness for two of them. The question now is, can we measure this difference? Namely, can we give an upper bound to the number of false alarms? This paper provides an answer to this question.
We introduced the notion of epsilon partial completeness. As you can see here, we still have incompleteness, but this time the result between the abstraction of the concrete function and its abstract interpretation is bounded by an epsilon amount, and this imprecision is measured by a distance. So our framework still strictly depends on both the abstract domain and the distance shows. Given a concrete domain, a concrete semantics, an abstract domain and an abstract semantics, and an input, our question is, can our program analysis be epsilon partial complete? This means that if our program analysis is epsilon partial complete for program P, then it must be partial complete for all program Q. We define a new class of programs for which this property holds, and we call this class the partial completeness class. Given an abstract domain and an epsilon bound, if an element of our abstract domain has larger error and this holds for all epsilon, then we say that the abstract domain has unlimited imprecision. We prove that this is true. If this is true, then there always exists an epsilon partial incomplete program, namely a program which makes the analysis imprecise above all epsilon. The second question we want to answer is the following. Can we prove whether a program analysis has bounded imprecision with regard to a given program and input? Formally, given a program, an input, an abstract domain, a distance over it, and an acceptable bound epsilon, can we build an analysis verifier that answers yes if the input analysis is epsilon partial complete for that program and input, while no otherwise? And note that this is equivalent to checking whether the program is in the corresponding partial completeness class. Unfortunately, the answer is no, and this is the consequence of the non-recursive enumerability of the partial completeness class of programs. However, we proved that for abstract domains that satisfy the ascending chain condition, the partial completeness class turns recursive enumerable. This means that we can at least answer yes if the program is the corresponding partial completeness class. Although the partial completeness class is in general non-recursively enumerable, we introduce a proof system which is able to infer an overestimation of the imprecision accumulated during program analysis.
Why it matters? So we all know that completeness is an important property, but unfortunately it is hard or even impossible to achieve. Our framework provides a way to estimate the error of the analysis, and in this way it can be used to guide the researchers in order to choose the best domain with respect to the degree of imprecision that they want to have. Our proof system is able to type program analysis, thus providing an upper bound on the error of the analysis with respect to a given program. This is very useful when we deal with code obfuscation, namely with these transformations that are designed in order to degrade the precision of static analysis. And the potency of code obfuscation can be measured by measuring the degree of imprecision that it induced on the transform program with respect to the imprecision that we have on the original program. All the details can be found in the paper, and I'm sure you will enjoy reading it. Thank you for your attention.